Hello, everyone. My name is Monica Villarreal, and today I will be presenting on piles and pile equipment for the fall 2025 course, Fundamentals of Commercial Construction Systems at Texas State. I chose this topic because although I work in the solar industry, where pile driving is a major scope of work, I don't have a lot of experience on it, and this would be a great opportunity to learn more about the topic. This is the outline for today's session. We'll start with an introduction to piles and their purpose in construction. From there, we'll look at the different pile types and the equipment associated with their installation. Then we'll move into cost and safety considerations, followed by how piles are specifically used here in Texas. Finally, I'll summarize the key takeaways, provide references, and close with a few test questions to check your understanding. So what are piles? Simply put, they're deep foundation elements. Instead of relying on shallow soils, which can be weak or compressible, piles transfer loads down to stronger soil layers or rock. They're designed to resist not just vertical loads, but also lateral forces and uplift, like those caused by wind or earthquakes. That's why you'll often find them under bridges, high rise towers, and offshore platforms. Without piles, much of our heavy infrastructure wouldn't stand. In short, piles are essential for providing deep foundation support and stability in challenging soil conditions, making them a reliable way to ensure the structural integrity of buildings and other structures. When we talk about types of piles, we can look at them in a few different ways: by construction method, by material, by function, and then a few special cases. By construction method, the first group is driven piles. These are pre-manufactured piles, timber, steel, or concrete, that get hammered or vibrated into the ground with a pile driver. The big advantage here is that the driving process actually compacts the soil around the pile, which increases load capacity. The other method is board piles, also called cast in situ piles. For these, a hole is drilled, reinforcement is placed, and concrete is poured right on site. These are more flexible. You can go larger in diameter and deeper in length. They're also much quieter and produce less vibration, which can be very helpful in urban areas. By material, piles can be timber, steel, or concrete. Timber piles are the oldest type, often used in soft soils and for things like jetties. Steel piles can be H sections or hollow pipes. They're strong, can carry huge loads, and you can easily extend them by welding. Concrete piles come in two forms: precast, which are made off site and then driven, or cast in situ, which are formed right in the ground. By function, we have end bearing piles, which transmit loads straight down to a strong soil or rock layer, and friction piles, which work by developing resistance along the sides of the pile through skin friction with the soil. Finally, there's some other types worth mentioning. Sheet piles are typically used as retaining walls, more about holding back soil or water than carrying structural loads. Helical piles or screw piles have helix-shaped plates and literally screw into the ground, which makes installation fast and clean. And composite piles combine materials like steel section on the bottom for driving and a concrete section on top for durability. So as you can see, there are numerous types of piles, and the method, material, and type all depend on the soil conditions and what the project requires. Here you can see a visual representation of the main pile types. Piles come in different shapes depending on project requirements, things like soil conditions, the loads they need to carry, and how they're installed. The most common shapes are round and square, each with distinct advantages. Round piles are often preferred because they are installed more easily, match the natural shape of drilled holes, perform well in soft or marine soils, and distribute vertical loads efficiently. Square and H piles, on the other hand, offer different strengths. They resist lateral loads better, develop more skin friction along their flat faces, and penetrate dense soils more effectively, making them a great choice for tougher ground conditions. Pile installation requires specialized equipment, and the setup depends on whether piles are being driven or drilled. For pile driving, two types of hammers are most common. Impact hammers deliver repeated high energy blows to drive the pile downward. They can be powered by diesel, hydraulic systems, or compressed air, and each has different performance and environmental considerations. For example, hydraulic hammers allow more control over energy levels, while diesel hammers are more portable but much louder. Vibratory hammers work differently. Instead of striking, they use vertical vibration to reduce friction between the pile and the surrounding soil, allowing the pile to slide downward. This makes them ideal for sandy soils or temporary installations where piles may need to be extracted later. For drilled piles, the equipment is specialized for excavation. Rotary drilling rigs bore vertical shafts, often with augers or buckets, which are then reinforced and filled with concrete. Continuous flight augers rigs, or CFA rigs, streamline the process. They drill into the ground and simultaneously inject concrete as the auger is withdrawn, which minimizes collapse risk in soft soils and speeds up the installation. Support equipment is just as critical. Cranes are used to lift piles from the ground or transport position, aligning them vertically and guide them into the leads for driving. Load testing devices, such as static load test frames or dynamic monitoring systems, verify that piles have achieved the required bearing capacity. Without testing, it would be impossible to guarantee that piles are safe for the loads they'll carry. On the right, the diagram shows how all of these elements come together in a pile driving rig setup. The crane and the boom position the pile in the proper location. The leads act like rails, keeping the hammer and pile perfectly aligned throughout driving. At the top is a hammer, which delivers the energy to advance the pile, cushioned by the hammer cushion and pile cushion to reduce wear and protect both equipment and material. The helmet fits over the pile head to distribute the hammer's force evenly. Midway down, the pile monkey helps hold the pile steady during driving. At the bottom, the pile gate and brace ensure the pile remains in position as it penetrates the ground. This system shows how multiple components must work together to ensure piles are installed safely, efficiently, and accurately, and why proper equipment selection and setup is just as important as pile design itself. Pile installation costs are shaped by several key factors. One factor is the pile type. Driven piles are usually more economical on repetitive projects, while drift shafts are more expensive because they require slurry, reinforcement, and longer installation times. Another factor is the installation method. Driving tends to be faster and more efficient, while drilling is slower and requires specialized equipment. Mobilization of heavy equipment is also a significant expense. Moving cranes, hammers, or drilling rigs to site and setting them up can be costly, especially in remote areas. Labor costs add up as well. Skilled operators and crews are essential for both driving and drilling, and efficiency in the field has a big impact on costs. And finally, testing and inspection contribute to the total. While these add to the budget, they're essential to verify that piles meet design capacity and prevent costly failures down the line. The chart on the left shows the cost breakdown example for driven steel H piles compared to drill shafts. For driven piles on the left, the biggest expense is material, followed by installation. Mobilization, labor, and testing are relatively modest. For drill shafts on the right, the costs are much higher across the board, especially material and installation, which make up the largest share. That's because drill shafts require more concrete, reinforcement cages, and slower, more equipment and test installation. Mobilization, labor, and testing also add up, but the big takeaway is clear. Drill shafts can easily cost more than twice as much as driven piles, mainly because of the material volume and installation time. Pile installation is one of the noisiest and most hazardous operations on a construction site. In fact, let me play you a quick audio clip of pile driving in a solar farm so you can hear what it's like. Please take a moment to adjust your volume if necessary. As you can tell, it's incredibly loud, loud enough to cause permanent hearing damage without protection. That's why hearing protection is mandatory on every site while pile driving. But noise isn't the only concern. Vibration from pile driving can affect nearby structures, and the heavy equipment involved, cranes, hammers, and drilling rigs, pose risk if not carefully managed. Crews also face hazards from flying debris, falling objects, and working at heights. To manage these risks, safety protocols include full PPE, regular rig inspections, and clearly defined exclusion zones to keep people out of harm's way. Pile installation can't be considered successful unless it's done safely. Texas is a great example of how piles adapt to local conditions. For bridges and highways, driven piles, steel or concrete, are common. In Houston and the Gulf Coast, where clays are soft and water tables are high, drilled shafts are the standard choice. Out west, in renewable energy projects like wind farms and solar fields, we see a lot of screw piles and drilled piers. And in cities like Dallas and Houston, skyscrapers depend on deep drilled shafts to deal with expansive clay soils. In the next slide, I'll specifically cover the installation process for solar. The process for solar pile installation follows a clear sequence. It starts with ground testing and the geotechnical report. Test piles are driven in different soil zones and borings are analyzed. This stage can reveal two big risks: corrosion and rock refusal. If the soil shows high corrosion potential, the design will call for galvanized piles to prevent premature deterioration. If refusal is encountered due to shallow rock, then instead of driving, piles have to be drilled and filled with slurry. In other words, the geotech results drive what kind of piles are selected for the project. Once design is finalized, the next step is procurement. Solar projects typically use steel piles ranging from 6 to 10 feet embedded length through though longer in softer soils. These piles are ordered in massive quantities and fabrication details matter, whether they're galvanized, cut to the exact dimensions, or slotted for racking attachment. All of those design factors directly affect the overall cost of the project. The piles then move into distribution. Shipments arrive in batches, and piles are staged around the site. To avoid confusion, piles are often painted at the ends to indicate type or length, and distribution maps are created so crews know exactly which piles go where. This helps avoid costly mistakes when thousands of piles are being installed across hundreds of acres. Installation is the most visible step. A solar farm uses several types of piles: inverter piles, array piles, transition piles, and dead end piles, each with a specific function in supporting the racking and electrical equipment. Piles are driven with specialized machines such as the Vermeer PD10, Geik rigs, and Orteco drivers. Because pile driving is both noisy and high impact, crews must wear special PPE, including double hearing protection and metatarsal guards. Accuracy is critical here, as piles must meet strict tolerances for plumbness and embedded depth to keep racking in line. Finally comes testing and remediation. Random piles are proof tested or pool tested to ensure they meet design capacity. If a pile fails the pool test, it has to be pulled out and reinstalled by casting in place with slurry, even if it wasn't originally installed that way. For remediation, common fixes include cut and weld or push and pull alignment repairs to correct piles that are out of tolerances. These steps ensure that by the time racking is installed, every pile on the ground is structurally sound and compliant. To wrap it up, piles are critical when shallow foundations just won't cut it. We've got several types: driven, drilled, screwed, and composite, and each has its own equipment and use cases. Costs can vary a lot depending on method, and safety is always front and center because of the risk involved. And here in Texas, we see all of these pile types depending on the region and the project. The big takeaway is that piles are what let us build heavy, complex structures on less than ideal soils. Here you can see the references used for this presentation. All right, quick check before we close. First question: what is the main reason piles are used instead of shallow foundations? Because surface soils are weak and we need deeper support. Which equipment is most suitable for driving steel H piles? Vibratory or impact hammer? Why are drill shafts heavily used in Houston and coastal Texas? Due to clay soils and high water tables. If you got those correct, you've got the key ideas. Thank you, and this concludes the presentation.